Hey everyone, so today we're going to go through a couple of different things. So first, let's talk about generalized linear models. So the entire concept of generalized linear models falls under the idea of what is the distribution of a response variable. So typically in linear regression, as we've talked about before, the response variable follows a normal distribution. So if we have a linear regression, that's mu I equals beta times plus beta 1x. This is typical linear regression. With y, our response variable, it typically follows a normal distribution of mu and sigma squared. But we know that there's going to be other types of scenarios where that's not the case. Sometimes we're dealing with count data. Sometimes we're dealing with a data that's more left skewed or right skewed. Perhaps it's more of a gamma distribution or even Poisson distribution if we're dealing with count data. So we know that there could be or even binary classification problems. We could be working with a Bernoulli distribution. So we know that there's many different scenarios in which the dependent variable or the y variable is not a normal distribution. So how can we account for these different distributions and these different length functions? We'll get into what length means later on. But how can we account for these different distributions of the response? Well, one way to do this is through generalized linear models, and that's why we have this entire generalized linear models in the first place is to account for different distributions in our y variable. So let's go into what this actually means. So first, there's three different components to a generalized linear model. First, there is the distribution of the y. So as we talked about, could in this case, it's in the case of linear regression, normal. In the case of Poisson regression, it follows a Poisson distribution. We'll go into what logistic regression is, and that follows a Bernoulli distribution. It's also gamma, and we'll go through what are their common distributions, and specifically for exam PA. So first is the distribution of y. Second is the length function. So the length function is how the mean response of the y variable relates to the linear predictor. So we have the length function. So the length function is the relationship between the linear predictor. So this is our linear predictor, our beta naught plus beta 1x, or in the general form, it would just be our beta times x. Right? This is our linear predictor. What is the relationship between our linear predictor and our the mean of our response variable? So that's our length function. So you can think of this as if we have g, some g of mu equals some function, right? So if it's mu, then this is what we call the identity link. And this is the case in linear regression. So why is it called the identity? Because the expected value of the y variable is the linear predictor itself, right? So in this case, the expected value of y is beta naught plus beta 1x, right? So it's the expected value of the y variable of the response variable is the linear predictor itself. But there's many other cases in Poisson regression and in logistic regression where that's not the case. So we also have this function which relates the mean of the response to the linear predictor. So we have log of mu over 1 minus mu. So this is saying that the log of mu over 1 minus mu, that is equal to the beta naught plus beta, or beta 1x in this case. Okay, so this is the relationship between the relationship between our linear predictor and our mean expected value of our response variable. And so let's go through a couple common distributions and their length functions. So first we have Bernoulli. And typically instead of log, like you'll just see natural log. So we have Bernoulli distribution, the canonical link. And when I say canonical link, you can think of that's just like the common link. I won't go into how that's actually derived, but you can just think of this as for this distribution, if y is distributed according to this distribution, then the canonical link or the typical link function that's used is this. So for Bernoulli, it's a natural log of over 1 minus mu. For normal, it's just the identity. So that's just mu. For gamma, it's 1 over mu. For inverse Gaussian, it's 1 over inverse Gaussian. It's 1 over mu squared. For Poisson, it's 1 over mu. And this mu represents the expected value of our response variable. So the log of the expected value of a response divided by the 1 minus the expected value of the response, that equals the linear predictor. So this is where, again, to reiterate, we're establishing a connection between what the mean of the response variable is and the linear predictor itself in identifying this link function. And the first requirement for generalized linear models, the first thing that we want to have is the distribution of the y. What can we figure out in theory? What's the distribution? What are the points that we can have in terms of the data for the y variable? So if it's test scores, we can probably expect that to be a normal distribution. Again, depends on the problem that you're trying to solve. If we have like the number of people visiting a store, that's probably more of a Poisson distribution. We maybe something like the time it takes for X task to be done, maybe that follows like a gamma distribution or something like that. But depending on the problem, depending on the context, the distribution, the response variable is going to be different. And then you can figure out your link function. And there's also some cases with your distribution, depending on this problem that you're actually solving, the distribution and the link function. You don't necessarily have to use a canonical link. So there may be cases where your distribution could be Poisson, but then for some reason you think that the relationship between X and Y is actually linear relationship. And the link function, you can think of the link function as like really the relationship between our linear predictors. So in this case, if our general trend, like if we expect, so you can think of this as like, let's say this is exponential, right? Or I guess we can think of this as normal. Yeah, that's actually linear regression. Let's see how we want to do this. Let's say that follows an exponential distribution, right? This is an exponential distribution. Right? So maybe we know that the link function should be like natural log of something, right? But then we also know that, let's say for some reason we determine that the distribution of our y actually follows a normal distribution. Right? We see that the distribution of our y actually follows a normal distribution. So for each of these points, that's actually the expected value of the normal distribution of the y at that given point. So there's certain cases like that as well that we want to be mindful of, in which we're not always using the canonical link function. Let's go through a couple of different things here. So we talked about common link functions, maximum log likelihood, and I'm not going too much in depth with this, but I just want to like relay like the high level overview of this. So we have max log likelihood. What this refers to is, you can think of this as the accuracy of the model. So the likelihood that the model and its parameters match the data. So we want to have a higher max likelihood. You can think of this as I said before, the accuracy of the model. The higher the max log likelihood, the more closely that our model matches the fully saturated model. And we'll get into more detail on what that actually means. So it's the likelihood that the model and its parameters match very closely with the data itself, right? And you don't want to have it too high of a max log likelihood, because that means that is a potential sign for overfitting as well. So typically we have a log likelihood of the null model, which is the intercept only model, and then we have a log likelihood of the saturated model, which takes into account all of the parameters, all the predictors in the model. Typically, the model that we come up with is somewhere in between these two. Okay, so we can say that this is the log likelihood of this model. And again, if it's very close to this saturated log likelihood, then that's not necessarily a good thing. That's a potential sign of overfitting as well. And then deviance is how far the log likelihood of our model is from the saturated model. So we have that saturated minus the log likelihood of our current model. So this is our model, and this is that of the saturated model. So we want to have a small deviance. A zero deviance means that these two are equal, which means that the log likelihood of our model is equal to the log likelihood of the saturated one model, which is a potential sign of overfitting. Okay. And I just want to go back. Like another way of seeing this is like just I just want to provide another way just for visualization purposes. So the log of the mean of the response variable equals the linear predictor. So this is in the case or natural log in the case of Poisson regression. Okay, that's the case. Just want to like provide another sort of perspective to a way to think about it. Okay, let's see. Now, in generalized linear models where betas are estimated using maximum likelihood estimation, I won't go through the exact formula. So, what values of beta do we have in order to maximize this log likelihood function? And then let's see. We know AIC and BIC. So we talked about AIC, BIC before. So here it's almost the same formula. So AIC equals -2 times the log likelihood of our model plus 2p, the number of predictors. BIC, -2 log likelihood of our model plus natural log of the number of observations plus the predictors. As we mentioned in the previous video, this is going to penalize the number of predictors more. So yes, we could have more predictors. It's yes, we could have more predictors. It's gonna The only thing is this is gonna be heavily penalized. So in general, as we mentioned before, BIC is the metric that's going to in general have fewer predictors when everything else is the same. Okay, so adding more predictors, right? So adding more predictors would increase our maximize log likelihood. Okay. Let's see. Let's see what we also want to give here. So as the number of predictors increases, our training log likelihood is going to increase. Our training deviance is going to decrease. Our chi-square statistics won't really get into that, and then our will decrease, and then training RMSE will decrease. And we also have negative binomial distribution. So typically, for count data, we use Poisson distribution, but there's some situations where a Poisson distribution, so one of the assumptions of a Poisson distribution is mean is equal to variance. If for some reason you don't think the mean of your response variable is equal to the variance of your response variable, if you think, for example, it's actually lower, then that's a potential consideration for you to use actually negative binomial distribution, which is still a discrete distribution. It's a discrete distribution on non-negative integers, similar to Poisson, and it models count data. And whenever some of the assumptions, and specific the assumption of the fact that the mean is equal to the variance is not met, and you think that there's reason to suggest that the mean is actually less than the variance, you want to use negative binomial. And there's this cool little formula that you want to have in terms of like modeling purposes. So if y given lambda follows a Poisson distribution centered around lambda, but then that lambda also changes according to gamma distribution, then then the distribution of y we know is negative binomial. So if the mean, let's say the mean fish count, let's say you're modeling like the fish count. If the mean fish count stays constant, that's Poisson. The mean of the lambda is not changing. But let's say the mean of the fish count actually changes randomly, and the how it changes, it follows a gamma distribution. The mean actually changes the gamma distribution. Well, then the mean fish count actually follows a negative binomial distribution. So again, in these scenarios, you want to make sure that you're not just using Poisson distribution just because it's count data. You want to really make sure, does the mean equal the variance? Is the mean even actually changing? If it is, it might be possible that it's actually follows a negative binomial distribution, and that might be a better distribution to model the scenario after. So that's just a brief overview of like common link functions in general, generalized linear models, and like the entire concept of that. Now let's get into just NFL predictions, I guess. So week 3, I think the best predictions, I think Jets money line minus, I think it was 350. And let me just check. Yeah, minus 350. Oh no, minus 260 actually, minus 260, minus 260. And the reason is, so this is going to be my only prediction of the week here. My best prediction of the week. Feel pretty confident about this play because Jets lost like the first game of the season, and they bounced back in week 2. Momentum, I feel like they're gonna win a couple, win some games here in a row now because they lost in week one as like a bounce back. And then last week, the Thursday night game, it was an upset. The Bills upset the Dolphins. Back to back Thursday night upsets are very, very rare. I don't think, yeah, they rarely ever happen. Jets are the favorite this week against the Patriots at home, home opener too. So I think Jets money line minus 260 is a good value play here. I guess not value play, but I'm pretty confident in it just in terms of like it hitting. And then let's see a couple of things. Still believe in like the Aaron Rodgers MVP season, right? Week one we saw uh, him losing, the Jets losing. And then week two bounce back, similar to 2014, similar to like even like 2022 when he lost to the Saints, and then bounce back MVP season. So still, that trend is continuing. The other additional trend rate that we mentioned was 2018 Mahomes, 2019 Lamar wins MVP, then 2020 Rodgers won MVP. We're sort of seeing like the same sort of trend where Mahomes won it, and then last year Lamar won it, and then this year probably Rodgers. Okay, and then a couple of other things want to go over. So Parkinson's law is one thing I want to go over that I've been trying to implement. So the entire idea of Parkinson's law is that typically, like in the nature of work, the nature of human work is really you can spend like an abundant amount of time on really any given task. Right? We have very limited time, and so we really want to take advantage and have awareness of the time that we actually have. And so how can we do that? Parkinson's law takes that into account. Whenever we give ourselves like, let's say like 10 minutes or even an hour to do a task, it might not be the best quality, but we're going to finish that task in an hour. Whereas if we give ourselves an entire week to do that same task, it's going to take us an entire week. If we give ourselves a month to do that same task, it's going to take us the entire month. So the time that we give ourselves to do a particular task, it's going to take that amount of time, because our mind will increase the amount of things that we have to do. The task will grow in complexity and perceived complexity within our minds. And I think one of the time management skills I've learned is really allocating your time to spend on each sort of activity rather than be like, okay, I'm just going to complete this today. No, spend like 30 minutes on this, then move on to this, then move on to this. What I've also noticed is that it also helps in your energy and happiness levels as well. Whenever you spend like 5 hours on like a single problem or like a single task, then it really just drains your energy and you're not as productive. Whereas if you spend 30 minutes on one task, switch 30 minutes, switch 30 minutes, then your sort of brain gets like almost a reset whenever you're switching tasks for every 30 minutes, not every like 5 minutes or so, but after a reasonable period of time, your mind gets a break. You're working on more things, and sort of the effect of Parkinson's law is also in play here, where you're setting a fixed deadline. You're allocating a certain portion of your time to do a particular task, and even to like finish a task. That could be like a game that you can play in your mind as well. So yeah, those are a couple of things I wanted to go over today. We went over like generalized linear models. We went over NFL predictions, Jets money line week three, obviously, and then we went over yeah, deviance, maximum log likelihood, the crux of generalized linear models, and Parkinson's law. So yeah, that's it for today, and I'll see you in the next video. Thanks.